Hello everyone, and welcome to MAE334's Lab 2, in which we'll go over RC and RLC circuit analysis. My name's Will, and I'll be taking you through the introduction of this presentation. The experiment begins with calibrating the given values of resistance, capacitance, and inductance with an LCR meter. For quick changes, decade boxes were used to set up each of the values. So the purpose of the experiment was to monitor the voltage responses over the capacitance for RC and RLC circuits. Through experimentally determining the results of the voltage gaps, we can calculate other helpful information such as the time constant, damping ratio, and natural frequency. And this information is helpful because it's not just limited to RC and RLC circuits. It can be applied to almost any dynamic system.
The equipment used for this lab consists of decade boxes, LCR meter, data acquisition board, and a software named LabVIEW to analyze the step response. The decade boxes set the resistance, capacitance, and inductance for the circuit, which can be adjusted using physical dials. Of course, there is some discrepancy between theory and real circuits, which is why we use a LCR meter. An LCR meter reads the inductance, capacitance, or resistance of a circuit, which gives a more accurate representation of what the values actually are, since the decade boxes are not entirely accurate. This results in more accurate calculations when comparing theory to real-world circuits. Once the decade boxes are wired to the data acquisition board, the experiment was underway. We recorded a step response using LabVIEW and saved the data for further calculations.
Let's now look at the results and their significance. Observe on the left the results of the RL circuits. The blue indicates the supply voltage, whereas the red and yellow indicate the actual and theoretical voltage across the capacitor, respectively. Theory was close to reality for both voltage and tau. Tau is estimated around 0.008 seconds by three different methods. One of these, the error fraction method, estimated tau as the negative inverse of the slope of the orange line in the right graph. You can see in the left graph that by adding an inductor to the circuits, a large sinusoidal response was induced. This, however, was eliminated by solving the governing ODE and changing the resistance such that the roots of the characteristic equation had only real parts. The right graph showed that this worked.